all of human history, we humans have always wanted to colonize the cosmos. But doing so will require unimaginable amounts of energy. Luckily for us, the sun is the perfect place to get the energy. It's 100 quintillion times more powerful than the most efficient nuclear reactor on Earth today, shining with the energy of 100 trillion nuclear bombs per second. But getting the energy is not so easy. Oh, and we're not talking about getting 50% of the energy, or some of it. We're talking about all of it. This video was mentored by Karun Thunderver from UVic and Peter Scott from NASA's JPL. Thanks to both for helping me on this project. Throughout human history, events have happened that boosted our energy output as a species. We electrified the world with the Industrial Revolution and the discovery of nuclear power. Alan Turing invented the computer, and we entered the information age in the mid-1900s. No wonder that in the future, we'll probably gain complete control of the Earth's energy and resources. A Type 1 civilization. And so after that, we'll try colonizing the universe. But space is huge, and the fuel needed for such a feat is unbelievable. But I just mentioned a Type 1 civilization. What is a Type 1 civilization? And it comes from the Kardashev scale, named after Russian astrophysicist Nikolai Semyonovich Kardashev. Duh, я говорю по-русски. Kardashev came up with a scale that explains how advanced a civilization is. A Type 1 civilization can harness all the Earth's energy, or 10 to the 16 watts. That is also equal to 2.778 times 10 to the 9 kilowatt hours. It's easy to get here. Simply transition to fusion, hydroelectric, renewable, and antimatter energy. We'd probably get there in 100 to 200 years. That's decent. But then we advance more. A Type 2 civilization can store 10 to the 26 watts. That is also equal to 2.778 times 10 to the 19 kilowatt hours, which means capturing the entire output of a star, which seems like sci-fi nonsense, but to get there, we can feed stellar mass into black holes, use star lifting, which is getting rid of matter from a star to use it for other purposes, use antimatter, or collect parts of the energy of multiple stars. But the most viable, or at least the one that I'll be talking about, is a Dyson Sphere, which is explained soon enough. We'll probably get to a Type 2 civilization in a few thousand years. A Type 3 civilization can capture all of the energy of a galaxy. Again, sci-fi nonsense, but nothing's impossible, so we might get there. A Type 3 civilization would use 10 to the 36 watts. That is also equal to 2.778 times 10 to the 29 kilowatt hours. How could we get there? One option is to build multiple Dyson spheres around multiple stars. There are other options too. We could use gamma ray emissions, or use a black hole bomb to collect the energy of a supermassive black hole and or quasar, giving us a galaxy's worth of energy. Getting here could take 100,000 to 1 million years. A Type 4 civilization would capture the entire energy of the universe. Absolute madness. Our good old drug Kardashev didn't even mention a Type 4 civilization. He thought it was too advanced. A Type 4 civilization would use 10 to the 46 watts. That is also equal to 2.778 times 10 to the 39 kilowatt hours. I would think about continuing the pattern about how to do it by collecting the energy from multiple black holes. That is, building multiple black hole bombs around multiple black holes and quasars. Or possibly, maybe harvesting dark energy and dark matter. After all, they make up 95% of all the universe. Only 5% of the universe is ordinary matter. But getting here would probably take tens to hundreds of millions of years. That's my guess. Type 5 Earthlings would become gods, manipulating the multiverse as they please. Clearly, humanity will almost never hit a Type 5 civilization. The only way I would think of doing it is by harvesting the dark matter and energy from multiple universes. That'll probably almost be hit when the universe dies trillions of years in the future. Type 6 civilizations are people who can literally manipulate space and time, traveling to the past and the future. Getting there will probably take forever. I will guess that probably some of the black holes will have started to evaporate by that time. Speaking of universe death, in fact, I'd say a very intelligent species can escape a real dying universe, trillions of years in the future, by using the energy from the Type 4 civilization to artificially cause a Big Bang, creating a baby universe, a window to escape the dying universe. Now there's an equation that you can use to calculate the Kardashev type using the total wattage. Created by the one and only Mr. Carl Sagan, this is the equation. K equals log P minus 6 over 10, where K is the Kardashev type and P is the total amounts of watts used. In 2018, the human race used 18.40 terawatts of energy, or 5.1 million kilowatt hours, which if we plug that into the equation is approximately a type 0.726 civilization. Not the worst, and we're actually making noticeable progress. Since in 2012, the wattage of humanity was 17.54 terawatts, or 4.87 million kilowatt hours, which is approximately a 0.724 civilization. Which means that in only 6 years from 2012 to 2018, we increased our Kardashev type by approximately 0.002. That should not be so surprising with new technologies coming here and there, but it's quite good to be able to prove that we're making progress, especially when you consider that the Kardashev scale is logarithmic. So, we're making considerable progress into a Type 1 civilization, but when we do get there, how will we get to a Type 2 civilization? The way we'll do that is by capturing not some of the sun's energy, but all of it. How do we do that? With a Dyson Sphere. A Dyson Sphere is a megastructure that surrounds a star and captures as much of its energy as possible, turning it into useful energy. It was first mentioned in the 1930s in a sci-fi novel, which described a structure encompassing the star. The novel was called Star Maker by Olaf Stapleton. But then in the 1960s, Freeman Dyson described a Dyson Sphere, but he didn't talk about how to build it in his paper, which led a lot of people to think that it was just a hollow shell, but we'll get to that later. So, the Dyson Sphere actually comes in different flavors. They are a Dyson Sphere, which is usually any variation other than these is typically considered a Dyson Sphere. So this is a model of one of my possible variations of a Dyson Sphere. It's physically impossible, but we'll get to that. It's basically a mirror. There's going to be mirrors up here, but I left only half of it so we can transparently see the sun. And the energy will be beamed from the thing into somewhere else, like the moon, for example. But it's physically impossible. Why? Because it's so hard to get the materials in the first place. We need to obliterate entire solar systems. Now a Dyson shell, a uniform solid shell of matter. It's also kind of impossible. It's impossible because there's no material near strong enough to handle all these pressures, so it will just collapse. But even if it could, it would be very vulnerable to impacts and could cross straight into the sun. A Dyson belt, or Dyson ring. A ring or multiple rings of independent energy collecting satellites. A Dyson ring is a single ring of them, and a Dyson belt is a set of rings that orbit at different distances. There's obviously going to be more than 2 rings, but I just decided to put only 2 so that we just would have more time. A Dyson swarm is the same as a Dyson belt, except the rings are at different angles. Or you could think of it as just a swarm of satellites that surround the sun with tiny gaps that orbit the sun. A Dyson bubble is like a Dyson swarm, except the satellites don't orbit the sun, but rather keep themselves stable. So which is most viable? It'll probably be the Dyson swarm, since it is low cost and very efficient. The only thing is that it will not be any easy task. A huge Type 2 civilization ain't simple. If each satellite was 1 square kilometer, which let's assume they are, we'd need 30 quadrillion to surround the sun. And if they're built as light as possible, we'd need 82.32 quintillion tons of material. Assuming all that, how could we build such a structure? We'll divide the building process into three main things: materials, design, and energy. To get the materials to build a Dyson Sphere, we'd need to disassemble a whole planet. Of all the planets, Mercury is the best candidate. It's close to the sun, very metal-rich, has no atmosphere, and only a third of the Earth's gravity, making it comparatively easy to launch things into space. The design of the satellites is important too. We need something that has no required repairs, very long lifetimes, and is inexpensive. They're most likely going to be huge mirrors that reflect light, similar to the mirrors on the James Webb. They'd be light, made of polished metal foil bound to some supports. And once they do collect the energy, they will refocus it to central collecting stations, like say possibly on the moon if we're living there at the time, which could then beam the energy to Earth through hyper-advanced microwave technology. No, not a microwave oven, a microwave wave. And no, not that kind of wave, this wave. A microwave wave is a wave with a wavelength of 1 millimeter to 1 meter. That's weird. It's weird how you say that many waves. A microwave wave is a wave with a wavelength. That would make for a really good tongue twister, don't you think? But the thing is, we also need lots of energy to build a Dyson Sphere. Like, you might as well almost need a Dyson Sphere to build one. So to get all this energy, we need to automate a bunch, like as much as we can on Mercury. Ideally, there would be a small crew of people, or possibly artificial intelligence, that oversee all the machines doing the actual work on Mercury. There are 4 pieces of technology we need to get this energy: solar collectors, miners, refiners, and launch equipment. The solar collectors will collect the energy needed to do the work. We might start by deploying 1 square kilometer of them in orbit around Mercury, either as mirrors or traditional solar panels. They will power the miners, which mine the surface. But this leaves a question. What elements will the miners mine? To answer that, we need to know what the mirrors would be made of. The mirrors on the James Webb are usually made of beryllium. And if there's no beryllium on Mercury, we can instead look for magnesium on the surface, which can also do the trick. Mercury is made of many elements, as revealed by MESSENGER, NASA's probe. The surface composition contains potassium, thallium, and more elements. And the mantle is also made of some silicates: silicon dioxide, titanium dioxide, and the core is also made of iron, nickel, carbon, silicon, and sulfur. This means we can extract the magnesium to make the mirrors. So the refiners will extract those elements, the magnesium, and fabricate them into the satellites. To launch them, we need to find a way of launching them into space that is inexpensive and easy to reuse. The rockets we know today will not work and aren't very useful for this. They're too expensive and difficult to reuse. So instead, we'll probably use a sort of electromagnetic track that launches the satellites at high speed, taking advantage of Mercury's low gravity. And because of its low gravity, we only need to launch the satellites at 4.22 kilometers per second. There are 2 ways to do this math, but I chose the former, which is using the ratio of Earth's gravity to Mercury's gravity to find the ratio of Earth's escape velocity to Mercury's escape velocity. The second one is easier and works if you don't have that much memory of random numbers. But we also need to find an advantageous location on Mercury to launch the satellites. Unlike on Earth, it's actually not better or worse to launch near the equator, since Mercury is tidally locked, and therefore one side is always in daylight and the other is always on nighttime. So the daylight area will be a shorter path to launch the satellites to the sun, and therefore we can pick there. And then we can start launching the satellites. The satellites will be packed tight for launch, unfolding like this once they're in orbit. How much energy will the panels collect? Solar panels today are typically 15 to 20% efficient, but the efficiency of solar cells can reach 42%. The entire panel is at most 20% efficient, which means that since the sun produces 3.846 times 10 to the 26 watts per second, or 1.068 times 10 to the 20 kilowatt hours, that means at max efficiency we capture 5 times less useful energy, or 7.692 times 10 to the 25th watts, or 2.137 times 10 to the 19 kilowatt hours per second, which is a lot. And if we use solar cells, we can capture just over 10 to the 26 watts, or just under 4.5 times 10 to the 19 kilowatt hours. Now, the way solar panels work is that the panels are made of silicon cells, a metal frame, a glass casing surrounded by a special film, and wiring. The solar panels absorb the sunlight during the day, and in each solar cell is a thin semiconductor wafer made from 2 layers of silicon. One layer is negatively charged and the other is positively charged, forming an electric field. This is like a battery, where one terminal is negative and the other is positive. And when electricity flows, it flows from the positive terminal, through the negative terminal, through the circuit, and back to the positive. When light energy from the sun strikes a solar cell, it energizes the cell and causes electrons to loosen from atoms within the semiconductor wafer. Those loose electrons are set into motion by the electric field surrounding the wafer, and therefore this creates an electrical current. It's basically a coal-free way of making electricity. And this means that it's actually a misconception that the solar energy is turned into useful energy. It's the motion. It's not that. It's that the solar panels are dependent on the sun to make electricity using the loose electrons. Anyway, after we launch our first satellite, we'll take advantage of exponential growth, using the current parts of the swarm to build more infrastructure on Mercury and launch new satellites faster and faster. One panel helps make the next one, then 2 become 4, 4 to 8, 8 to 16, 16 to 32, and so on. After doubling 55 times, the sun would be completely surrounded by 36 quadrillion satellites. 6 quadrillion more satellites than we need. And this might be finished quickly. If one panel takes a month to build, we could have finished the entire Dyson Sphere in less than 5 years. Now, we'd probably have to build this in the next few thousand years, according to Michio Kaku, like I mentioned at the beginning. But will we have the technology by then? Well, today we're starting to develop some of the technology for this, but governments are too focused on political issues that have no use in humanity's progress. We need leaders that are interested in harvesting the progress that we all dream of, because big progress requires big ideas. And in 1,000 years, we will most likely already be multiplanetary, living on Mars and the Moon. We'd be able to control the weather, as a Type 1 civilization would do, but as for our population, how many people will there be? Because there aren't many projections of population that go beyond 2100. Even a 2002 UN paper only goes until 2300. But by the year 3000, the Earth's population might be 12,951,226,948 people, according to a video by Imperial Statistics about the world population by the top 25 countries from the year 1000 to the year 3000. And while there will be people on Mars and the Moon, obviously, there will of course be less than 13 billion people on either of these, since both are smaller than Earth, which is quite obvious. But actually, after building a Dyson Sphere, we can also host living habitats, like what's called an O'Neill ladder state. Each O'Neill ladder state could have 1 trillion people, and another rotating habitat called a Mercury ladder state could have 1 trillion to 1 quadrillion. To surround a sun, that could use millions of O'Neill ladder states, or a few thousand Mercury ladder states. That could fit a few quintillion people in one Dyson Sphere. And in life, we only need to make sure there's enough space, like personal space and food and air for all of us. So using a spherical planet is mostly a waste of material, and therefore an O'Neill and Mercury ladder state would just work fine. This structure is really important, since it would explain how we can do many more amazing things, like colonizing planets and becoming multiplanetary, or creating huge living spaces like the ring world, which contains ladder states I just talked about, turning planets into another blue home, or even moving to other stars and becoming interstellar. A Type 2 civilization would thrive after building such a structure. We can even dodge a danger, like a supernova, by moving the sun using a stellar engine, which steers a star through a galaxy. And in fact, let's return to our good old friend Kardashev and calculate the type of civilization. If we return to the power output of this civilization, 1.068 times 10 to the 20 kilowatt hours, that would make us approximately a 1.989 civilization. And if we captured just under 4.5 times 10 to the 19 kilowatt hours, then that would be a Type 2.02 civilization. A mathematical proof that a Dyson Sphere can get us to a Type 2 civilization. Absolutely awesome. Thank you, math. But the big worry is, Are there enough materials on Mercury? Thankfully, even Mercury is so massive that it has 3 times more material than we need. That is, we'd need to disassemble a third of Mercury. Although that does require a lot of energy, it's still possible. In fact, physics is whispering at us. If we're advanced enough, it's an easy process. Many astronomers think that there are Dyson Spheres out there in the galaxy already, because it is so important for any life form to expand beyond its home planet. In fact, we almost found a Dyson Sphere around a star named Tabby's star, or this particular name, but unfortunately, we later confirmed it was just a set of asteroids and comets. While I can't guarantee you that we'll ever get here, if we do it, we'll have complete control of the solar system. So to conclude, building a Dyson Sphere is hard, but worth it. It requires energy, but it's quick. It's costly, but useful. It requires big ideas, but it's a big progress. And most of all, it requires the mindset of mankind, but it is the yes to long-term survival. If we do it, we'll embark on a Type 2 civilization that will thrive forever. Freeman Dyson would be proud.